Okay, hello everybody. Thanks for sticking around until the end. So the last talk of the conference is going to be on value classes in Scala. So I'm just going to explain what we have right now, what we maybe could have in the future. And so my name is Lukas. I'm working for TypeSafe in the compiler team. I stay in Switzerland with a few of the other TypeSafe guys. So value classes were introduced in Scala in 2.10, so that's almost 1.5 years ago. And I just took this part of the release notes, which says, a class may now extend Anyval to make it behave like a struct type, and then there's a comment restrictions apply. So I will explain you what Anyval is all about. So Anyval is an existing thing. I will explain you what it is and how that thing fits together. And of course, this comment restriction applies makes an interesting topic for a talk. So here's the agenda. So first, I'm just giving a quick introduction to value classes. You've already heard quite a lot of that in previous days. I'll go through an example and show you how the Scala compiler transforms that into bytecode. Then I'll show you how this whole value classes integrate into the type hierarchy of Scala. And I'm going to spend quite a bit of time on limitations and feature interactions. All right. So the main idea of a value class, you already heard, is that the instances are inlined. That means they are represented at runtime as simply their fields. So there's no object that is allocated on the heap, and that of course saves space and at the same time reduces the load on the GC. The other main advantage is that the data is local, so it's on the stack or directly in the array, hopefully, and you don't need to chase pointers. And, well, you can do stuff like that with arrays already, but so it's, of course, much more convenient for programmers to just write a class, create instances, call methods. So that's the main idea. So what's the implications of that representation? So the main thing is that on the JVM, the object identity is linked to having an object. So if you represent values simply as their fields, you lose the ability to have this object identity. And there are certain things that you cannot do anymore. Most notably, you cannot synchronize on values, and you lose some stuff like this identity hashcode method and things like that. And the other main consequence is that values, like the fields of a value, are not mutable. And the main reason for that is because they are copied around. If you pass a value to a function, then a copy is created, and it would be very surprising if you could mutate that copy and not mutate the original thing. So by definition, value class fields are always immutable. Good. So here are some of the use cases. The first one is the one that I'm going to show you in a larger example, so it's okay if you don't understand immediately how it works. In Scala, we can have extension methods, so you can add methods to any existing type, and value classes allow us to do that without any overhead. Other common use cases are bit fields, so in the Scala type checker, we have a mode bit field where you can have various modes active at the same time, and that is a value class. Flags right now, which represent like modifiers, I think they are currently not a value class, but I guess they could be. Other use cases, like you can have semantic primitives, so you can create classes like meter and mile, and then these two are distinct types, and you cannot mix them up while keeping all the performance of having a simple integer or a simple double. And you can also come up with new numeric types, for instance, like something like a complex. So one example that was implemented not by us, but in a library called Spire. It's a library for numerical computing written in Scala. They have an implementation of complex, which is called fast complex, and it bunches two float values into a long. And yeah, this is pretty performant compared to having two objects on the heap. So you already realize maybe that all of these use cases require a single field. So that's the current main limitation we have in Scala. So a value class can only have one field. All right, so that that was the introduction. Now we are going to look at this example that I promised. So the example is extension method. So maybe let's first look at the line at the very bottom. So in Scala, in order to create a tuple of two values, you can use this arrow syntax. And the arrow there in the example is simply a method call. So it's string dot arrow and in parentheses the other string. It's exactly the same thing. And so the string class in Scala is the same as the string class on the JVM, so it doesn't have this arrow method. So the way this works is through an implicit class that is in scope. This implicit class is defined in an object that is called predef. So this predef object is automatically imported into every Scala program. So that's part of the standard library, so everything that's defined in predef you will have in scope. And this implicit class, I changed the name a little bit to have it fit on a slide. This arrow class takes one argument. It's a value of type A, so it's generic. And it extends Anyval, that means it's a value class. And it has this only method, which is the arrow, which takes another parameter and returns the tuple. So what happens, how does this work, is that while type checking this expression that you see at the bottom, before actually issuing an error and saying the arrow method doesn't exist, the Scala compiler, the type checker, goes off into what we call an implicit search. And in this case, it will search for a conversion from string to anything that has this arrow method, right? And it will see that, oh yeah, we have this implicit class in scope, so if I wrap the string into the arrow class, then I do get the method, and that's how the thing works. Okay, so yeah, the first part we're going to look at the declaration of this arrow class and see how it's transformed by we're going to check some of the stages of the Scala compiler pipeline. So first, parsing, well, nothing is happening here, basically. You get the implicit class. Well, something is happening, namely, instead of having a class parameter, so before we had a class parameter of arrow, now you have one field, and you have a constructor that is generated by the parser, and this constructor takes exactly the same arguments as before the class would have taken. And this arrow method is unchanged. Now, part of this transformation for value class is done by the type checker. So you can already see that the implicit modifier on the class, it disappeared. And instead, at the very bottom, we get an implicit factory method. So that's just a generic transformation for implicit classes, because that concept only exists in the language very early. So the implicit search mechanism will never look for a class. It will always look for a transformation method. And so the transformation method that we get is this arrow factory method that just takes any value and creates an arrow instance. Then what else changed? So the field is the same. What we got is an accessor method for the field. So in Scala, fields are never accessed directly through field reads, but always through getters. So this one was also introduced during type checking. And otherwise, oh yeah, of course. So the initializer and the arrow method are simply type checks and resolved. And finally, the type checker also adds hash code and equals methods. So that's part of the specification of value classes, is that the Scala compiler or the language compiler will always add hash code and equals methods that simply compute the hash code for all the components and equality. Okay, so there's one new compiler phase that was added for value classes. It's called extension methods. And what it does is that it moves all implementations of methods in a value class to a companion object. So the companion object, you see it in the lower part of the slide, has the same name as the class, and it will hold the same methods, basically. You can think of companion methods in a companion object as static methods in Java. It's really quite similar. So for every method in the value class, a new method is generated in the companion object. It takes one more parameter, which is the receiver. And then the actual implementation ends up in this companion, and the original method that we had in the value class just forwards to that. All right. And then the final part of the transformation happens in type erasure. So here we have quite a few things going on, and I will just go through them top to bottom. So some of these transformations that I show here are generic. They happen independent of value classes, and they happened before. And some of these transformations are new, and they were introduced due to value classes. So first thing erasure does, it removes type parameters. So the arrow of A class becomes simply arrow. And all references to the A type parameter within the class, they become erased. They get erased to object. Okay. So the field that you have in the arrow class will be a field of type object, which can hold anything if we box. All right. Then for the so for the extension method that we have down here, initially it would take, so the receiver object that is passed as argument, it was initially of type arrow of A, all right? So now, let me think which way around. Yeah, so now the new transformation that kicks in first is the value class transformation. And it says, okay, I have a reference array of, I have a reference to a value class, doesn't matter if it's generic. And each reference to a value class the type is replaced by the underlying value. So the underlying value of the array, of the arrow class was A, right? So we would wrap a value of type A. And that's why the erasure phase first translates this arrow A reference to A. And then, of course, because A is not was type parameter initially, so this is then further erased to object. So it means the value that we pass to the extension method is unwrapped, and it's no longer an an arrow instance, but it's directly the objects that used to be stored in the value class. That's today, yes. I mean, you could put a tuple into such an arrow class, and then you just would get a tuple, like a two-field object today. But of course, you could think of a transformation that just creates two parameters instead. Yeah. All right, and then, so because we replaced the receiver, so the instance by its underlying value, all the accesses to the fields have to be rewritten. So while before we used to read the A field from the arrow instance, now we just use the field, the instance directly because it's already the value that you want. And the last thing that the erasure transform does is it removes boxes where it can. So the implicit factory method, it used to create a new arrow box, right? And that is unnecessary because the values are represented as the underlying value. So this implicit conversion simply becomes identity. Okay, so to understand how this all fits together, we just look at the actual use side, so how the use side gets compiled. So instead of having the interpreter, I put the same expression into a small class here, and into a single method. And after type checking, so what the type checker does is it converts the string into an arrow instance using the implicit conversion, and then it calls the arrow method on it, right? And the rest is done by the erasure phase, namely, whenever the erasure phase sees a method invocation where the receiver is a value class, it will rewrite the method to call the extension method that was generated in this companion object. So basically, it knows that this arrow method is implemented in the companion object. It rewrites the call, and this call to the factory method actually is still there. It's not eliminated by the erasure phase, but it doesn't matter because it's not creating an actual instance of the arrow class. Because, as I showed before, the factory method is simple identity, so it just does nothing. Okay, and If you turn on the optimizer in the Scala compiler, then a bunch of inlining would also go on here, and not today, but in theory, we could easily end up with a simple call to the tuple constructor. All right. So now I'm going to go a bit more in detail how we added this value class into an existing language. So that's more of a type hierarchy discussion. So first of all, the restrictions that apply. So a value class may not have fields in Scala. I mean, that's a syntactic thing. It may not have syntactic fields, but all the fields have to be constructor parameters. And right now, it's a single one. You cannot have an initializer expression, so you cannot not have any side effects within the body of the class. Then, as I said before, the wrapped values may not be a value class today. So that's a restriction that we think could be lifted. It's just not yet implemented. So right now, you can only wrap non-value classes. But you can wrap, of course, primitive types. The hashcode and equal methods are provided by the compiler, and they cannot be overridden by the user. I don't think that's a strong restriction, like a necessary restriction, but it was, I actually don't know the details why this was chosen to be like that. And finally, well, we already saw this a few times. Value classes are defined by extending this Anyval type, which is a predefined type in Scala. And now we're having a look what this actually means exactly. So the type hierarchy in Scala has a few built-in non-real types, but that just exist in the type system. At the top of the hierarchy, you have any, and then you have these two types, one called Anyval, which is a supertype of all primitives, and on the other hand, you have Anyref, which is a supertype of all reference types. And by defining a value class as a subtype of Anyval, you actually have a few nice side effects. And the thing is that primitive values like int and also primitive classes that you define as a user, you cannot assign null to such fields or to such values. And in Scala, we can rule out this possibility directly in the type system, because null is a special value that has this type here, null, okay? And null is only a bottom type of any ref, but it's not the bottom type of any val. And if you try to assign the null value to a parameter or a field which has a parent of any val, you will get a compile time error. And similarly, values cannot be used to synchronize, okay? And in Scala, synchronization is like a selection on an object, and that object has to be an anyref. So if you have a value, an anyval, then you simply don't have synchronization available by the type system. All right. So now you might wonder, so one thing that you see is that all user-defined classes and also traits are subtypes of any ref. And that means if you define a value class, you cannot actually implement the trait. Okay? And we wonder what's the reason for that. So the reason for that is traits in Scala, they may have fields, and they may also have like initializer statements. And this is just not suitable for value classes because it wouldn't apply to the restriction that we discussed before. But of course, we would like to share code between value classes, and maybe even between value classes and ordinary classes. And for that reason, Scala 2.10 also introduced the notion of universal traits, which are traits that extend any. And I'll show you this here. So universal traits live kind of in the middle. And by the type system, they don't have access to synchronization. And then a universal trait can be extended both in a user-defined reference trait or in a value class. All right. So for the rest of the talk, I'm going to go in a few examples of what we cannot do and how things work in practice. So first important topic is boxing. So there are a number of situations in which values of value classes are automatically boxed. So this happens whenever you assign a value to one of its supertypes. So if you assign an instance of a value class to a universal trait, or to Anyval, or to any, the instance is boxed. Okay. Boxing also happens whenever you put a value into a data structure, so into a generic data structure. You could, of course, specialize the data structure, that would work. But if you use a value class in a generic position, then the Scala compiler will box all the instances. And well, we hope that eventually value classes and specialization that might work together, but we haven't really worked on this yet. And finally, one of the really sad restrictions is that values stored in arrays have to be boxed. And the problem there is mainly we couldn't keep the correct semantics otherwise, because if you have an array of ints or an array of a value that erases to int, the two really look exactly the same at runtime. It's just an array of int. But the language specification requires us to be able to distinguish the two types using instance of test, right? So there's not much we can do except boxing whenever you put the value into an array. Okay, there's one more situation when boxing occurs, namely whenever you invoke a method that was inherited from a universal trait, from a parent. And I'm just going to illustrate why this is the case. So in this example, we have a super trait, which extends any, so it's universal. It has an accessor method x that's abstract, and it has some method f that just accesses x, right? So now if we compile a method t1 that takes a super as argument and invokes the f method, that needs to be a virtual call, because the trait super might be subclassed by arbitrary reference classes and might be overridden a few times. So that really needs to be a virtual call. And well, now on the other hand, if we extend the super trait in a value class, then well, we actually know that there can only be that specific invocations, but there are a few problems. So first of all, the way the code was written, the code for f was emitted, it assumes to have this instance, right? So the code for this method here, it also does a virtual call to look up the x. And let's say we have these two types under separate compilation, then there's really not much we can do. Right? And for that reason, every time you invoke a method that was defined in a parent, the value is boxed first. And might be, of course, if it's possible that the virtual machine might optimize these object allocations. But would be nice to elevate them. All right, so why is boxing so bad, right? Of course, because it's slow. And it's not only because it's slow. The other problem is that in Scala, when you have some code that uses value classes, it's actually quite difficult for the programmer to see where the boxing occurs and where it doesn't. So I explained you already the main situation where it occurs. And the thing is, people that use value classes, they want to write high-performance code, and they need to know quite a lot of these details of the implementation and of the limitations in it, just in order to be able to work around the boxing. And yeah, so that's kind of a problem. On the other hand, we could say that in Scala, we already do kind of favor the uniformity of the code over the performance. So a few examples are while and for loops. So if you write a while loop or a for loop in Scala, it's actually a very different thing, the way it's compiled and the way it performs. At least today, we hope to optimize for loops, of course. And another example is that you can put primitives into any collection, and all the primitives obviously will be boxed unless you use specialization. And programmers that write high-performance code, they just need to know these kind of things. And they need to know a little bit more when they use value classes. Okay, So now we look at a few restrictions that are not imposed by the language, by Scala, but more by the platform. So one thing is overloading. So if you have two value types that erase to the same underlying type, so here you have a meter and a mile, then you cannot create an overloaded method between those two types, right? Because they would have exactly the same signature. So you do get the compile time error, thankfully, and it doesn't just crash at runtime. But well, in many cases, you can work around it quite easily. Like you just have to choose different names for the methods, maybe. But there are a few situations where there's this situation with bridge methods which is quite unfortunate, where we cannot do much, actually. So in this example, we have a value class C, where the underlying type erases to object. So it's generic. So in the bytecode level, the values of type C will be represented as objects. Now we have a generic trait A with one method that just returns A, okay? So the erasure of the F method also returns an object, all right? So now if we create a subclass K of this trait, and we specialize the type of F, so we create an implementation of F that returns a C. Now, unfortunately, the C of object here, it erases to object. And the Java spec requires us to generate a bridge method as well. And this bridge method, unfortunately, has the same signature, right? And for that reason, you cannot do this. So yeah, from time to time, if you create value classes that wrap objects, you run into this situation. We realized that you don't run into this situation for anonymous functions. So there was a bug that was fixed. So this problem can only happen if you actually create a named function. But if you create an named class, an anonymous class or an anonymous function, you don't run into this problem because you can just rename the implementation method, and because you know it will only be called, so the thing will ever be only called through the invoke interface. That's kind of a detail. All right. So one thing we would like to do in Scala is, in a value class in Scala, is extend the Java interface, because Java interfaces, like, they seem to have all the restrictions. They don't have fields, they don't have constructor statements, right? But the problem is that today in Scala, an interface that comes from Java, it's a subtype of any ref. So you can do things like call synchronized on a Java trait, on a Java interface, right? And in order to allow subclassing Java interfaces in a value class, you would have to change the supertype of the interface that comes from Java to any, and this would be source incompatible because you couldn't do this thing anymore, right? And well, the answer there is we didn't do it, so you cannot use a Java interface as a parent in a value class. And unfortunately, we needed some hacks because, for example, if you create a case class in Scala, then it will always extend the serializable interface from Java. And in order to allow value classes to be case classes, we had to kind of hack around it and say, okay, serializable is fine. And we did the same thing for comparable, but this is not the real solution, of course. Okay. Then one discussion that came up, of course, in the mailing is this: can we make option of T a value class? And again, it's not straightforward, unfortunately, because if you have a value of type option of T, it can have a number of shapes. So it can be null. The value can be null. It can be none. So so in Java, you only have one class optional. In Scala, we have a trait option and then two subclasses. One is sum of x, and the other one is empty, none, okay? So it can be either a none or it can be a sum of something, and if it's a sum of something, it can be also a sum of null, right? And the problem is if we make this, let's say if we make sum a value class, then, or option a value class, then all of these things kind of erase to null, right? And sum of x erases to x, and so that obviously doesn't work. We cannot reconstruct what we had originally. And maybe just to explain why we need this sum of null, which looks a little bit dubious, I have to say. But you can do stuff like this in Scala. You can create a collection that contains a few values, a string, and also a null. Okay, and then you can call find on it, and you say, I want the value that is null, and what you get back is an option. So the find method returns you an option if it's, success if it finds something, otherwise none, and in this case, it returns you the sum of null. Yeah, so for that reason, well, the option is not yet a value class in Scala. Okay, so this slide is a bit more high level, so it's just saying like, well, of course we had a few implementation issues adding this thing to the Scala compiler. There are rough edges basically when features interact, and there's today also still a number of open bugs, so this list reads like value classes plus type bounds, compiler crash, value classes with a method that has a lazy val, crashes compiler, value classes with a method that's private this, crashes compiler. So it's, this is just to show that changing this representation also in the type system has implications which are kind of hard to foresee or which break existing assumptions. So I guess that's a normal state of affairs that you have to live with in an existing system. All right, so to finish up, what would you like to have in the future? So of course, one of the main things that we would like to have is value classes with multiple fields. So we could do it today on the existing VM. So the idea, as John asked, we could certainly flatten out values with multiple fields into multiple parameters or multiple locals. The problem, obviously, is when you return, then today there's just no good solution. So the easy thing is to just create the box and return the box. And did I miss the slide? Yeah, so we are not sure if the effort that we put into this solution there is really worth the return that we would get out of it, because there are so strong limitations that we cannot overcome without any support from the VM, that it's difficult to judge, right? So two more issues. Of course, we still have the problem of needing to box when you put the values into an array. Well, maybe one more discussion, I think it came up also before in this workshop, is when you have multiple fields and just represent them as multiple locals, then you have the question of what happens if you assign to such a variable in terms of atomicity. And more future work. So of course, we would love to integrate value classes with specialization to get collections, so generic collections that don't need to box their values. And of course, once support in the virtual machines comes along, then we will be very happy to rebuild our implementation on top of that, and we can profit from a lot of things. So we can profit from having arrays of values. You can have return values. We can also be compatible with the rest of the ecosystem. We wouldn't have this discrepancy between reflection anymore. If you create a value class, then suddenly reflection looks different and things like that. Okay, so that's it for me. I'm happy to take any questions. Yeah.
So is there anything in what you've seen of the value type work in the JVM coming that would suggest whether you would or wouldn't be able to migrate your implementation to use the VM value types as they've been described when they arrive?
Right. I've read through the document a few times, and from what I saw, I think I haven't seen anything fundamentally that would disagree with what we are doing and what we would like to do as well. I think we can also accept minor changes of semantics or minor changes of restrictions in a major language release when we use such a change, right? And so, we will certainly keep up with the developments. That's sure. Right?
Follow-up question.
Well, I'm not the concurrency expert, so yeah. There was the discussion, so today you already have the problem with longs, right? So in that sense, yesterday, exactly. So maybe that will change, right, in the future, or hopefully. And then if that changes, then it seems a bit more inconsistent to do something different for value classes. So to require the volatile for value class as well, not requiring it for anything else. But again, I think that's more a question for the people building concurrent libraries than I mean, the two choices are kind of there, right? So yeah. Okay. Good. Thank you.